Hello and welcome again to FlippedHarber for Calculus. In this video we're going to be talking about using the method of implicit differentiation in order to find the derivative. Our objectives for this lesson are to learn how to apply the method of implicit differentiation to find the derivative of a relation. Our outline for this video will talk about what implicit relations are. We'll talk about implicit differentiation using a couple different methods. They're very slightly and they each have their own intrinsic benefits. We'll take a look at some examples. Then we'll use implicit differentiation to find the derivative of an inverse sine. And then we'll end by taking a look at the derivatives of other inverse trig functions. So first of all, let's talk about what an implicit relation is. We're used to seeing equations solved for y, like y equals the square root of 4 minus x squared. This is what's said to be an explicit equation where y is equal to some function of x, and that's it. Y is alone on one side, everything else is on the other side. An implicit relation is where we have both of the x's and the y's working together. They're not really separated out. Now sometimes we can take an implicit relation and solve it for y. This x squared plus y squared equals 4 is the equation for a circle. I could solve this for y and it wouldn't be too difficult. But sometimes we can't solve them for y. So the method of implicit differentiation lets us deal with this. We could always apply implicit differentiation, but we really have to when we can't separate out that y and make it y equals some function of x. Now here is an example where we could not solve for that y. If I tried to remove the sine from the y that's on the right side of the equation, I would end up putting a sine inverse in on the other side, and that doesn't solve for the y. That just basically moves the trig function over onto the other y, onto the y on the other side of the equation. So I can't really solve for this explicitly. So I have to instead, if I'm going to take the derivative, I'm going to have to use this new method of implicit differentiation. So, implicit differentiation relies heavily on the chain rule. When you're doing implicit differentiation, you want to always ask yourself, what's the next layer for my chain rule? What's the next layer for my chain rule? And you're following the chain rule deeper and deeper into these things until you're finally taking the derivative of just a plain old x, or you're finally taking the derivative of just a plain old y. Now, we keep taking the derivative of these layers until we get to that single variable. And then in my method 1, not that this is like an official name or anything, when I take the derivative with respect to x, that is the derivative over dx, the derivative of x is 1, the derivative of y is dy over dx. Method 2, I take the derivative with respect to nothing. You don't see a bottom to this fraction. So when I do this, the derivative of x, I literally say is equal to dx, which means the derivative of x. When I finally take the derivative of that plain old y, I say, well, the derivative of y is dy. So this might make a little bit more sense as we look at some examples. I'm going to do some examples where we use method 1, some examples where we use method 2, and I'll talk about the benefit to this weird taking the derivative with respect to nothing. Now let's go ahead and take the derivative of this circle equation, x squared plus y squared equals 4. I could solve this for y, it wouldn't be that difficult. Y would equal plus or minus, basically the top and the bottom of the circle, the square root of 4 minus x squared. But let's use implicit differentiation. And in my method 1, that's where I'm taking the derivative with respect to x. So I take the derivative of x squared with respect to x, I get 2x. Now that's just following the chain rule. It's absolutely nothing new compared to what we've been doing. When I take the derivative of y squared, now again, this relies heavily on the chain rule. I think about the y as being inside. So that's my inside function. So I take the derivative, taking care of the square first, so the square comes down, becomes 2y, and that dy over dx is the derivative of the inside. And for my method 1, the derivative of y with respect to x is dy over dx. Over on the other side of the equal sign, I have a constant. Whether we're using method 1 or method 2, no matter what, when you take the derivative of a constant, you get 0. So now my job is to isolate, to solve for this dy over dx. So I've got to basically get it alone on one side of the equation. So the first thing I'll do is subtract the 2x over, and then I'll divide by the 2y, so my 2's cancel, and I find out that dy over dx is equal to negative x over y. So now my derivative has both x and y's in it. Now I'm not surprised because I started out with a relation that was not solved for y. It was an implicit relation, so it had both x's and y's. My derivative, not surprised that it has both x's and y's in it. Now let's take a look at using my method 2 to take the exact same derivative. So now I'm not taking the derivative with respect to anything. I really have to rely on the chain rule here, and I have to think about that x as being inside as well as this y being inside for my chain rule. So when I take the derivative, the 2 comes down, that power comes down in front, and this dx is the derivative of the inside. Move on to the y squared, the 2 comes down front, I get 2y, and then the dy is the derivative of the inside. Now the benefit for this is every single term in my method 2 should have a dy in it or a dx in it. It has to have one of the two. It can't have both. So a lot of kids actually like this method because it provides a little check along the way. Yes, I seem to have applied it properly because everything that's separated by a plus, a minus, or the equal sign has a dy or it has a dx. So now I've got to solve for dy over dx. So I'm just going to do algebra on this. I'm going to move my 2x dx over, just subtract it right over to the other side of the equation. And what I need to do is get this dx over here on the bottom so that it's dy over dx. And I'm just going to treat this as algebra. I'm going to just divide it over and get dy over dx. Now I still have to solve for that dy over dx. I have to get it alone, so I'm going to divide the 2y over, and I have dy over dx equals negative x over y. Again, exact same derivative. I should have gotten the exact same derivative. I started out with the exact same relation. So my method 2 as an example of implicit differentiation. So let's take a look at some more examples. So again, this is really useful for these equations, these relations where I can't solve for y or I can't solve for it easily. So I would not want to try to solve for this y. I actually could, this is going to sound weird, but I actually could using a quadratic formula. But don't worry about that. We're going to take the derivative of this using implicit differentiation. So here we take the derivative with respect to x. The derivative of x squared with respect to x is 2x. Now when I look at that second term, I have a product right here. I don't know why my pen's not working right now. Oh well. I have a product with x times y, so when I do the derivative here I have to think about the product rule. So that's why you see the plus y plus x dy over dx. That's using the product rule. The derivative of x with respect to x is 1, and then multiply times the y. Then I take the x and I multiply by the derivative of y with respect to x. Move on to the next term. We've taken the derivative of y squared, so we know that it's 2y dy over dx. And then on the other side of the equal sign, I have 0 because the derivative of a constant is 0. Now with this method, anything that has a dy over dx is going to stay on the left side of the equation. Anything that does not have a dy over dx is going to move over to the other side. So I have to subtract over the 2x and I subtract over the y. And then my next job is to factor out the dy over dx. So you see that I factored out the dy over dx to the back on the left side of the equal sign. And then my last job is to divide by that x minus 2y. And I get dy over dx equals negative 2x minus y over x minus 2y. Now, this derivative means the exact same thing that the derivative always means. Remember that the derivative is a fancy word for the slope. So, I can use this for anything that I normally would have. Okay, so let's take another derivative using method 1. I want to take the derivative of e to the xy, so I have a weird power on e. It equals tangent y, so I'm going to use my method 1 again where I take the derivative with respect to x. The derivative of e to some power starts out with the exact same thing. E to the variable power is its own derivative, but then I have to multiply by the derivative of that power. And again, x times y means that I've got to use my product rule. So I get y plus x dy over dx. Over on the other side of the equal sign, the derivative of tangent of something is secant squared of that same thing. So since it was tangent y, that turns into the secant squared of y. And then that dy over dx comes from the chain rule. I took the derivative of the inside. Now I have to multiply through my e to the xy. The reason I have to do that is I have to be able to add and subtract things that have the dy over dx, add and subtract things that don't have the dy over dx. So I've got to get everything down to simple addition and subtraction. If I've got multiplication, I've got to multiply it through. I've got to distribute to get rid of those parentheses. So I see two terms that have the dy over dx. They need to end up on the same side of the equation. That's just done through simple addition and subtraction. So I subtract over my e to the xy times x dy over dx. I want to get everything that has that fraction dy over dx over to the same side. And then I am going to factor out that dy over dx. So let's factor out that dy over dx. Just move it to the back of the expression and put parentheses around everything. And now I need to divide by whatever is in the parentheses. And there we have dy over dx is equal to the e to the xy times y divided by the secant squared y minus e to the xy divided by x. Can't really factor anything out. I can't really cancel anything top or bottom. So that's my derivative. Now let's take a look at method 2 with this exact same relation. Now I'm going to take the derivative not with respect to x, I'm going to take the derivative with respect to nothing. So when I take the derivative of x, it's no longer 1, it's dx. When I take the derivative of y, it's not dy over dx, it's just dy. Still have to follow my product rule when I take the derivative of that power. Still have to use my e to the variable power rule, still have to use my tangent rule. But when I take the derivative of x, instead of saying that it's 1 times y, it's now dx times y. Take the derivative of y, it's dy, and then multiply it by the x. And then over on the left side, the derivative of my inside is dy. Again, I have to distribute that e to the xy in. I have to get everything down to simple addition or subtraction so that I can move it back and forth in this equation. What I want to do is group stuff. Everything on one side needs to have the dx. Everything on the other side needs to have the dy. So again, I need to group things based on what they have for the derivative in them. Before I do that, I'm going to run my simple check. I have 3 terms separated by a plus sign and an equal sign. every term should have a dx or a dy. Nothing should have both. Everything should have one of those two. And I see that my first term has a dx, my second term has a dy, and the term on the other side of the equation, my third term, has a dy. So good, my check works. I think I'm on the right track. Now I'm going to start to group. I'm going to push everything that has a dy over to the right side. Doesn't matter if it's the right or left side. I just decided to put everything with a dy over to the right side. I'm going to factor out that dy. Over on the left, I'm going to factor out my dx. Not too difficult because it's just one term. It's already basically factored, but I'm going to factor out that dy on the right side, goes to the back, and I've rearranged stuff on the left side so that the dx is in the back as well. So I need to divide the dx over so that it's under the dy. And I also am going to need to divide by everything in those parentheses that's multiplying the dy. So I move the dx over under the dy. I move the secant squared y minus x e to the xy to the bottom on the left side. And there's my derivative again. Now let's use this method of implicit differentiation in order to find out what the derivative of an inverse sine is. So when we say y equals sine inverse x, you might be going, well, why do we have to use implicit differentiation? This is solved for y. Well, we don't know how to take the derivative of an inverse sine yet, so I can't just do that. But what I can do is change it slightly so it's the sine of y equals x. Basically, I moved that sine inverse over to the other side of the equation, made it a sine. I know how to take the derivative of sines, but now it's on a y. So now I have to use my implicit differentiation method. I get the cosine of y, because the derivative of the sine of something is the cosine of that same thing, times that dy over dx. I'm using implicit differentiation, so I have to think of that y as being inside, and I take the derivative of the inside. Over on the other side, the derivative of x with respect to x is 1. So I have cosine y times dy over dx equals 1. Divide the cosine y over, hey, I got my derivative. But since I started with an equation that's actually solved for x, I'd like my derivative to be some sort of function of x. Since I started out with a function of x, I'd like my derivative to be a function of x. So how am I going to replace that cosine y with some sort of function of x? And if you think back to your trig, there's actually a way to do this where we do triangles. Now remember, y is an angle. Cosines and sines and tangents operate on angles and spit out numbers. So if I think of the y as an angle in a triangle, I can set up my whole cosine is the adjacent over the hypotenuse situation, and then I'm going to take the cosine of this new angle in my triangle, and what I end up getting is the square root of 1 minus x squared. Now I'm going to go ahead and try to draw this. My pen's not working real great for some reason, but I'm going to try to draw this. Hey, it's working now. My right triangle, and y is an angle in that triangle. So I know that the angle y, the sine of it is x. So the sine of that angle is the opposite over the hypotenuse. So if the sine of that angle is x, that means that my opposite side is x and my hypotenuse is 1. And I'm setting that up from this sine y equals x. I'm setting up my triangle using that. So I need to figure out what this adjacent side is because I'm trying to take the cosine of y now. Well, Pythagoras told us a long time ago how to find this. So it's 1 squared, well 1 squared is 1, minus the other side squared, all under the square root. So the cosine of y now is adjacent over the hypotenuse, so it's just equal to the square root of 1 minus x squared over 1. Well, I don't need to say that over 1. So the cosine of the sine inverse of x is the square root of 1 minus x squared. Now, I could do a similar method for my cosine inverse and my tangent inverse. And I don't know, maybe I'll make you do that on a test or something. But here are our rules for the three basic inverse trig functions: the derivative of the sine inverse, the derivative of the cosine inverse, and the derivative of the tangent inverse. Okay, so that's it. It's time for you to try some of this stuff on your own, and I'll see you in class, and I'll see you online.